Hello, a very good afternoon to all of you in Suzhou in China, and welcome to the AI Expo. I would have loved to personally come and visit you in Suzhou, but due to the travel restrictions, I cannot be here. So I hope we try and organize something next year where I can physically be there. So in lieu of that, I will try and get you a presentation over video, and I hope you enjoy this. So let me start by sharing my screen, and hopefully you should be able to now start seeing my screen that I have shared now. Good. So let me start by introducing myself. I'm a professor of robotics at the University of Edinburgh. My name is Sethu Vijayakumar, and I also direct the Edinburgh Centre for Robotics. I'm also the co-program director for Artificial Intelligence and Robotics at the Alan Turing Institute in London. And today I want to talk to you guys about automation to autonomy. So we have always thought about robotics as a way of automating a lot of work that humans don't want to do, the dull, dirty, and the dangerous. But I think we have to rethink this definition of robotics. I now think of robotics as something where we use robotics as a tool for doing our everyday work in a much more efficient, in a much more safe, and in a much more productive, economically productive fashion. So robotics now, I start thinking of it as something which is more as a tool to help you do things better, rather than something which replaces a particular activity or a job that a person does. And that is really going to be the strand of the talk that I'm going to give today. So I don't need to convince the audience here that robotics is already playing a big part in different walks of our lives, all the way from traditional areas like manufacturing and assembly to very new areas that would not have been possible without robotics, including things like the space industry, things like underwater robotics for exploration of the underwater resources, the nuclear power decommissioning and maintenance industry, and more smart cities, autonomous driving, to the healthcare sector, where we have to deal with new challenges in the aging population, as well as in things like things like where we have an exoskeleton for support of people who've had a stroke. So there's been a shift in terms of going from traditional ways of doing robotics, like when you program a robot to mimic something that you show the robot to do or program it to do, to new research, both in laboratories and in factories, where we are trying to go towards significant more autonomy in the systems. In other words, where robots can start making decisions on its own. So that's great, but I think the next 10 to 15 years, and perhaps even going forward, the biggest challenge will be in trying to seamlessly blend between one extreme of teleoperation and the other extreme of full autonomy in the robotic systems. And this is what I call shared collaborative autonomy, where we can seamlessly move between those two extremes, depending on the task and even within a single task. And why do I say that this is important? Why is collaborative and shared autonomy important? So if you look at the examples that I have listed across in the slide, from all the way from prosthetics and exoskeletons to self-driving cars to things like nuclear decommissioning and humanoid robots, there is a scientific reason for going with collaborative and shared autonomy. The scientific reason is that the full autonomy in robots is still a quite big challenge because of many different factors that I have listed here. So we do not now live in a world where robots are in factories, but they are interacting with humans, with other robots, multiple objects. The real world dynamics are quite hard to model, and you have to work with human intentions, so user intentions, which is notoriously hard to predict. So these are the scientific reasons why we need to look at collaborative and shared autonomy. But there's also another socio-economic reason. You might ask, why do we want to use automation and robotics at all? And the socio-economic reasons for doing that is listed here. It's including things like improving the efficiency of man-machine teams so that we can make things a lot more smarter, customizable, and sustainable. Economically sustainable, as well as from a huge perspective of food security. With the growing demands, how do we do things more efficiently? There's also a big factor in terms of hazardous asset inspection in the new infrastructures that we are creating in our cities. On top of that, it's about dealing with challenges like healthcare in the aging society. And now, when all around the world we are facing this challenge, an emergency like in a pandemic, we have to worry about how can we deal with low-touch economy, social distancing, co-work, and robotics has a big role to play in enabling and disrupting the traditional supply chains and creating new ways of doing this. So I have listed both the scientific and the socio-economic reasons for collaborative and shared autonomy. So what I want to do next is, in the next sort of 5 to 10 minutes, give you examples of 4 different areas or domains that we already do excellent work in, especially in Edinburgh, in the UK, as part of the nationwide effort in deploying robots in challenging environments, what we call extreme environments. And one such example is inspection, repair, and maintenance of, for example, assets like the offshore oil and gas platform. So we have a project called the Orca Hub, where the challenge is to go from wheeled and fixed base robots to legged robots, which can then be deployed on platforms like what you just now see. So offshore platforms where the robot is operating in environments that are built for humans. So these are not specific environments that are doctored for robots, but these are environments that are challenging, steps, slippery surfaces. So the machine learning challenges and the control challenges arise from trying to do effective deployment of these robots in such challenging environments. So one of the things that we've been working on is something called whole body motion control. For example, in a live site where we want to test the integrity of some industrial structures, then we want to be able to deploy sensors very fast, very efficiently, semi-autonomously. So having human in the loop do this test, but not necessarily have the person be in close proximity to things that may be dangerous. So these are examples of whole body motion planning where humans can still give some high level goals, but the robot in this case deploys the actual sensor in a sort of collaborative fashion. So that's one of the ways of challenging the status quo and using robots in an effective fashion. Another area where I'm very interested in use of robots is in what we call dyadic collaborative manipulation. So this is, in simple terms, where humans and robots can collaborate with each other to achieve a collaborative task, like in a car assembly manufacturing setting. So this is some research that we've been doing in collaboration with the Honda Research Institute in trying to get humans and robots to work together. So this is specifically important in scenarios like this, where social distancing and COVID has forced us to think about working where if you've got 2 people in close proximity, the supply chain and the manufacturing setting has to be shut down. But if it's a robot and a human, then they can still continue to work together because there is no issue of social distancing. So we want to be able to take the technologies and move and disrupt settings in very interesting, new, challenging environments. And the next example I want to tell you about is a little bit of work that we're doing in very exotic domains like the space. So this is a collaboration with NASA on using robots for the next generation of stations, either in the space station like the ISS, on Moon, on Mars. So this is, there are two reasons for doing this. One reason is to make these kind of missions more cheap. Second is safety. So typically space missions are becoming more expensive and dangerous due to space debris. So we want robots to be able to do significant tasks that astronauts are doing. So one of the things that we're doing in our lab is taking a very complex robot, like a bipedal humanoid robot, and creating mapping, planning, and control technologies so that we are able to get very robust, autonomous, semi-autonomous behaviors while this robot is being controlled from either the space station, outside the space station, or it's being controlled from another planet like Earth while this is being deployed on either the Moon or Mars. So we are solving a small part of the puzzle in trying to make these things, planning and control, a lot more robust. And finally, the last example I want to give you is something in what we call shared autonomy in healthcare, where we are seeing increasingly, to address the challenges of the aging population, for people who've had a stroke or disability, we want to be able to deploy robotic systems to assist them in order to collaboratively help a person, for example, restore walk. So this is some images and videos from our lab where we are using exoskeletons to assist a person to walk more efficiently. And if you had a stroke or a unilateral weakness on one side, we are trying to test technology where the exoskeletons can adapt to the gait of the person in order to help them achieve a normal walk. So effectively do the job of a physical trainer or a rehabilitation person. So, and you can do this potentially after the right form factor in the comfort of your home. So those were 4 examples of areas I wanted to sort of highlight. Of course, there are many other examples, but I want to move tact a little bit and sort of get into the details of some of the machine learning technologies that are enabling us to address some of those big challenges. So just to summarize, because I have a short time today to talk to you guys, I want to summarize 3 areas where I felt that machine learning has made a huge difference. And we are now already in our labs, we are seeing how this machine learning technology is being translated to new advances in robotics. So for example, what you see here is an example where we want a setting where a robot is working in a remote environment, but a human is seeing a console on the right and controlling this robot. So what you see is what we call punctuated autonomy, where in the remote live site, a dual arm robot is navigating through a scenario, avoiding obstacles, removing debris, and making local decisions on its own in order to decide how to, move a debris, which arm to use, and use the local sensing to navigate across a complex, cluttered scenario. But a human is seeing the console that you see on the right, and the human is only monitoring and giving high-level goals. So the vision is that a person may be able to do this very efficiently and maybe even be able to control 5, 10 such robotic platforms simultaneously using some low-touch screens, a low-touch feedback, what we call punctuated autonomy. So the machine learning technologies that have enabled us to do this is things like perception for localization and scene understanding, adaptive planning, and safe actuation and interaction. And as I said right at the beginning of my talk, the aim is not to do either full autonomy or teleoperation, but be able to seamlessly shift between these levels of assisted teleoperation and autonomous behaviors very, very smoothly. And that is what is going to lead us to be able to deploy these platforms very successfully in challenging environments. So this is not new. In science fiction, in the kind of settings that we have seen, like the Iron Man, we've already had a vision of being able to operate multiple robots, multiple devices from the comfort of your home while minimizing cognitive load on the person operating it. So this vision has been around, but now we are finally seeing this being deployed because of necessities like the pandemic, like the new kinds of work that we want to do and more efficient economy. So I've got a couple of more slides, but this is one of the most important slides in my opinion, because I want to focus on what are the underlying open scientific challenges that a person may encounter for the next generation. And these are the 3 points that I want to make and point out to the audience there in terms of where should we be putting our efforts in. So the first one is, how do we make sure the technology is safe for things like dynamic human interaction, human-robot interaction? So you can do it in one of 2 ways. You can do this in software. So we are doing some work in real-time adaptation using things like model predictive control, so that things are very adaptive and reactive to changing environments. But the second challenge, that one of the key areas that we work on, is what we call compliant actuation. So where we are creating new kinds of actuators, new kinds of robots that have the ability to be inherently safe even before we put in the software. So in case there is a failure, we will not have catastrophic failures in terms of an injury. And this is very important. So this work on compliant, efficient actuation that we've been working on, effectively putting springs in between joints in order to be inherently compliant while still being accurate and safe. The second big challenge, in my opinion, is the trying to reduce the sim to real gap. In other words, we need what we call digital twins, technologies for training and testing in the virtual environment, so that we can do extensive experiments, collect data, do testing in digital twins, because we will never have the chance to collect enough data in enough scenarios to do extensive testing with real robotic solutions. So we're doing putting a lot of effort into trying to build realistic digital twins on which a lot of machine learning tools, a lot of testing can be done before testing on real world platforms. And finally, and this is a very important point, we have, as scientists and researchers, we have to build techniques that are verifiable and explainable. So for example, if something goes wrong, can we find out what is the reason for the failure of such methodologies? So that's why we are building technologies that are not just deployable and we say, oh, this is great because this works well. We need to understand the limitations of some of these methods. And that is when we will achieve the best kind of resilience, is when we say we understand the limitations and vulnerabilities of our deployed systems effectively, to understand where we should use and where we should not use it, and when something goes wrong, can we explain why this has gone wrong so that it does not happen again. So this is, in my opinion, the biggest challenges. So understanding limitations and vulnerabilities of the deployed systems. And finally, I want to conclude by saying that in this talk, I have not touched upon some of the other important questions we need to worry about in the deployment of AI and robotics technologies. So things like moral and ethical use of AI, so that people are not disadvantaged, a particular set of people or class of people are not disadvantaged. We need to make sure decisions that the AI systems make are unbiased, so that we do not have uneven economic distribution between communities. We need to make sure things are secure, because the more and more interconnected systems you have, there's a danger for things to be hacked, to be taken over. Ransomware is a big question. As I mentioned in my previous slide, responsibility and explainability for causal inference is very important. And the other thing is, when we talk about transferring control, so when do we transfer control? How fast do we transfer control? For how long do we transfer control? And when do we switch back control between the human operator and autonomous systems? And how do we seamlessly go between the shared autonomy systems? So this is extremely important in smart cities, in autonomous driving cars, and more in environments within even our home. And this becomes increasingly challenging when we have learning systems, because learning systems are hard to predict because things are constantly changing. So to address all of these things, we are both at the University of Edinburgh and at the Alan Turing Institute, and in my group, which I have put a link to the webpage of our group, we are addressing all of these challenges in addition to developing the new technologies, both in terms of the hardware and the software technologies in robotics and AI. So we are trying to tackle all of those things simultaneously. So you cannot build technology and push technology down the throat of a user without understanding and addressing all of these challenges listed on the slide here. So with this, I want to try and conclude here. And I hope you've had a good experience so far at the conference. I hope you enjoyed my talk. And unfortunately, I cannot be there in person. Otherwise, I would have loved to answer some of your questions. But please do check out the web pages of my group, of our university, of the Alan Turing Institute, to learn a bit more about the kind of work that we do. A lot of our publications are online and open source, so you can look at the technologies that we work with. And I would be very glad when the travel restrictions ease to come back to China and work with some of you guys on some of these exciting new technologies. So thank you very much for the opportunity to present at your expo, and good luck and Godspeed with all of the new initiatives that you're doing in China. I'm very impressed with the speed of progress that's happening there. So I will stop sharing my screen here, and I hope that you guys can find an opportunity to come and visit us at some point, but also wishing you great success with all the new things that you're doing as part of this new and bold initiative at the AI Expo in Suzhou. Thank you very much, and good luck.